momentum is conserved.
In every situation, even in a car collision, momentum, go, go.
Welcome to another virtual physics lecture. Today we're going to be discussing momentum and the different types of collisions in which momentum is conserved. Be sure to take good notes and let's begin. Let's first start by explaining what momentum is. We tend to use this term often in everyday language, especially in sports. But what is it? Well, momentum is basically the value of how much damage an object's mass and velocity can potentially cause another object if they were to collide. That's why we often say that a very massive object has a lot of momentum when it moves, or a very fast-moving object will also have a lot of momentum. Basically, something big and slow can have the same momentum as something small and fast. Overall, the formula we use to calculate momentum of an object is P equals M times V. Notice that momentum is represented by the letter P. M is for mass, V is for velocity. Because we are multiplying mass times velocity, our units are kilograms times meters per second. Some important things that we should know about momentum is that it is always conserved in collisions, which we're actually going to focus on in these later slides. Lastly, we also need to know that in order for us to change momentum, you have to have the same force applied over a period of time. Lastly, we also need to know that in order for us to change the momentum of an object, a force must be applied for a certain amount of time. Let's take a look at the various moving objects and their momentum. Notice that the train, bus, and car all have different masses and velocities, but their momentum is still the same. The massive train has a slow velocity, the low mass car has a greater velocity, and the bus with moderate mass has moderate velocity. Therefore, both mass and velocity equally affect momentum. Please note that because all of these objects have the same momentum, that means that the difficulty in bringing each vehicle to rest, or in other words, changing its momentum, will all be the same. However, the amount of impact that will be felt is actually going to be determined based on the amount of time that this impact takes place. This is to another concept that is often discussed in sports, especially by coaches when they're asking their athletes to catch the momentum of the ball in order to decrease the damage felt upon impact. In physics, we refer to this concept as impulse, which is defined as the amount of force applied for a certain amount of time in order to stop or change the momentum of the object. Imagine a car hitting a wall versus a car hitting a haystack. In both situations, the car has the same amount of momentum. Thus, an equal amount of impulse is required in order to change the car's momentum. However, just because the change in momentum is the same, in other words, impulse, doesn't mean that the force applied will be the same. It all depends on how much time was taken at that moment of impact. For instance, the force on the car due to the wall is large, but that force only acts on the car for a small amount of time. Now let's compare this to the same car moving at the same speed, but this time hitting a giant haystack. The force on the car will be much smaller now because the moment of impact takes much longer, thus more time. Overall, it's essential to know that momentum is always conserved. To illustrate this concept, we use the following formula that states that the sum of momentum before and after an impact will be equal. The total momentum of a system is going to stay constant, which means that the total momentum before a collision equals the total momentum after a collision. For instance, let's take a look at these two cars. They both have the same mass, which is 10 kilograms, but one has a velocity of 3 meters per second, and the other has a velocity of 2 meters per second. If I were to calculate the momentum of each car, all I would have to do is multiply their mass times their velocity. This would end up giving me for car 1 a momentum of 30 and for car 2 a momentum of 20. Now if I wanted to find out the total momentum between these two cars before they collide, I would simply need to add them up and come up with 50 kilograms times meters per second. Now let's say that these two cars now collide. Then based on the idea that the total momentum is always constant in a system, this means that after the collision, the total momentum would also be 50 kilograms times meters per second. Notice that both cars still have the same masses, but now they have different velocities from what they originally started with, thus giving each car a new momentum. However, when added, they still have the same constant total momentum. It's important to note that collisions may be seen in two different forms. For instance, when objects such as these two cars collide but end up bouncing off of each other, we call these elastic collisions. On the other hand, we may have objects that collide and instead of bouncing off of each other, they end up getting stuck together, such as these freight cars, and we call them inelastic collisions. We're going to discuss the two formulas that are seen with each type of collision. However, it's important to note that in both of these collisions, momentum is conserved. Let's take a look at this next example. There's a getaway car that is traveling at 20 meters per second, and it has a mass of 1,575 kilograms. But in the process, it actually crashes into a 45 kilogram highway barrel, which is at rest. If the getaway car is traveling at 18.9 meters per second after the collision, how fast would the barrel be moved after getting hit? So let's start by making a list of what we know. We know that before the collision, the getaway car, which we're going to label as object A, has a mass of 1,575 kilograms with a velocity of 20 meters per second, and that barrel, which we're going to label B, has a mass of 45 kilograms with a velocity of 0 because it was at rest. Okay, so let's look at the momentum that is involved before the collision. When we multiply the mass and the velocity of each object to find out the momentum, we find that object 1 has a momentum of 31,500 and object 2 has a momentum of 0. Then we just need to add up these two and it gives us a total of 31,500. This means that after the collision, we must have the same total momentum, which is why we're going to equal both sides to each other. Okay, let's see what we know about after the collision. Well, we know that the mass of object A is still 1,575 kilograms, but now has a velocity of 18.9 meters per second. And we also know that the barrel still has 45 kilograms as its mass, but we don't know its new velocity. That is actually what we're trying to figure out. So to do this, we must first figure out the momentum of object 1 after the collision, which is 29,767.5, and we add it up to the momentum of the barrel. But since we don't know the velocity of the barrel, we first have to solve it by subtracting on both sides by 29,767.5, giving us 1,732.5. And then dividing by 45, which would give us a final velocity of 38.5 meters per second for the barrel. This next example, a 1,950 kilogram police car has a velocity of 12.5 meters per second, and it rear ends a 1,500 kilogram sedan that is moving at 3 meters per second. After the collision, the two cars get stuck together. What is their final velocity? So let's start by making a list of what we know. We know that before the collision, the police car, which is going to be labeled as object A, has a mass of 1,950 kilograms with a velocity of 12.5 meters per second. And the sedan that we're going to label as object B has a mass of 1,500 kilograms with a velocity of 3 meters per second. Okay, so now let's look at the momentum that is involved before the collision. When we multiply the mass and the velocity of each object, we find that object 1 has a momentum of 24,375 and object 2 has a momentum of 4,500. Then when we add these two up, we see that the total momentum would be 28,875. This means that after the collision, we must have the same total momentum, which is going to be seen on both sides of this equation. Okay, let's see what we know about the after the collision. Well, we know that the police car and the sedan got stuck to each other after the collision. We can now see these two objects as one, which will now be called object A plus B, meaning that the new mass would be 3,450 kilograms, which is basically the sum of both cars. And we now want to know what is their new velocity as one object after the collision. Since we're trying to solve for this new velocity, we must divide by 3,450 on both sides of the equation, giving us a final velocity of 8.4 meters per second. Okay, so that's it for this video. Hope you guys took good notes, and I'll see you in class.
You take an object with mass and give it velocity. Keep talking, whoa, keep talking.
Then you get momentum where P is equal to mv.
I love equations, oh, I love equations.
Another thing to know is momentum is conserved
In every situation, even in a car collision, momentum, go, go.